Well, first of all, thank you guys so much for putting these grants together, for being here, for being part of this community. As you'll see, I think it is super important, and I'm happy to be here with all of you. So I'll get straight to the problem. So AI is growing the field of AI is growing so quickly and consumes so much energy that there simply isn't enough electricity to sustain its growth. What this means is, 15 years from now, if AI was left unchecked, you wouldn't be able to turn on the light bulb in your house because it would consume 100% of electricity. What that means today, realistically, is that companies like OpenAI, AWS, they cannot scale their data centers to match business demands because nobody can power them. Meanwhile, the entire history of evolution, step by step by step by step, has turned the human brain into the most energy efficient computer possible under the laws of thermodynamics, right? Like, this is crazy. Each one of us in this room right now has a computer in our heads more capable than the best supercomputers on Earth. And at least for me today, it's run off of like 2 yogurts and a slice of pizza, which is just way less than, top of the end supercomputers. So what we've done is we have built a supremely efficient computer that uses living neurons to provide compute. So at a very high level, and I'm happy to talk more about this with you guys afterwards, the way this works is we have neurons in a dish, we have an electrode array, so think like a Neuralink chip in that same dish that can stimulate the neurons with electrodes, it can receive the pulses. And because neurons naturally try and seek out the patterns that they sort of recognize, what you can do is by sending it repeatable patterns, they respond with repeatable patterns, and you can essentially program the neurons to do different things. So all you really need is to be able to code neurons with ones, zeros, and basic multiplication. And from there, you can do matrix multiples. You can basically code computation from the ground up, and that's what we're doing. So our goal is to build an exaflop scale biocomputer. Our goal is to, build the future of AI computation on a more sustainable matrix. And so, like, as a first example, we're based out of Altitude Labs, which is Recursion Pharmaceuticals biotech incubator. So one of our first goals is actually to just build a protein folding model that they can use, integrate with their systems for low energy compute. So on the team right now, we have myself, a former National Science Fellow. I have put $150,000 into the company so far. My background is really in using machine learning to scale up bioprocesses. So a lot of my former work was in scaling neural cell cultures into 100-liter bioreactors. We have Dana. She's a Harvard-trained computational neuroscientist. Dave was actually CEO of a different biocomputation company focused on electrical engineering, but he shut it down to join us. And then through our Recursion Pharmaceuticals connections, we have Travis. He previously built the world's 30th largest supercomputer. He's helping us figure out how to integrate our biological supercomputers with silicon supercomputers. We have Travis. He previously built the world's first phenotypically complete map of neurons, Recursion's NeuroMap. And together we've made actually quite a bit of progress. So what you see here is we're human-induced pluripotent stem cells that we differentiated into neurons and then 3D printed into a custom bioreactor. And for context, that's about the size of your standard pink eraser that maybe you used in grade school. Connected them to some brain-machine bioreactors, built a mixed biological and silicon neural network. And as our proof of concept study, what we've done, and we've done this 3 times now, is we trained the tissue to control its own bioreactor. So what that means is these tissues need nutrients in order to grow. And every time we provided them with nutrients, we also provided them with an electrical stimulus. After a couple weeks, we only provided the tissues with nutrients after they provided the same stimulus that we provided. So essentially, we got these tissues to spike in a certain pattern that would control when they get nutrients, and then they successfully kept themselves alive for 21 days. And for context, if they are not doing this correctly, they'll die in a matter of a day or two. So for 21 days, 3 times, we've gotten this to work. So what we're doing with this grant, what we're doing with the community is, that previous example was an example of what we call a bespoke biocomputation study, meaning we trained the tissue to do one task, and it very effectively did that task, for a month at a time, multiple times in a row. But what we want to do so that we can actually make an impact in sort of the broader compute community is to build a generalized biocomputation language, a generalized biocomputation transformer that can ingest data from multiple sources and provide meaningful output. So we've already gone, we've been coding this for a while now, but one of the things we're going to do with the funds is sort of wrap this up and then test it in the lab. Specifically, what we want to do is build a 1-bit LLM. If you're familiar with a tiny Shakespeare data set, we're going to feed it to the tissue and see if we can't get the tissue to respond with electrical pulses that we would recognize as sonnets from Shakespeare. So even backing up a bit, right? Like, there's not enough energy on Earth to grow compute. Neural tissues are the most energy efficient computer possible. So we expect this in the coming years to become a dominant paradigm in AI ML compute, which is kind of scary for a couple of reasons, right? Like from the perspective of alignment, from the perspective of AI rights, of biological rights, from the perspective of, one group of shareholders driven by profit motives controlling the future of compute, especially the future of compute where there's a lot of concerns of, to not mince words, torturing a sentient computer, right? So like, there's a lot of reasons that we need to be very, very, very careful about how we accelerate the future of computation through biocompute. So our equally big goal, the reason I'm here in the room right now is to meet with all of you. What we outlined in our grant objectives is to have conversations with the DAC community to really just figure out how can we build these frameworks, how can we build these structures such that, $200 million from now, the amount of money it might take to build this exaflop biocomputer when the people currently who have our majority shareholders are either minority shareholders or, whatever that structure ends up looking like. How do we build this technology such that it's ethical, such that it is safe, such that it benefits as many people as possible? So my ask for everyone in the community is, if you're involved with AI ethics, if you're involved with, thoughts around machine consciousness, around intelligence, just around how to build some of these structures for funding and putting guardrails that can last around a project like this, I think those guardrails are as or more important than the actual technology development, which is why we're here. So, here's my personal email, or my work email, daniel@intactis.bio. If you're in the field, please reach out. If you're in the room and have thoughts on this, I'm around for the next 2 days. Please come and talk with me. I truly think that this has the potential to be the dominant paradigm of computation in the future. And it's, as someone who is actively building this, it's very important to me that we build it right. So just looking for community feedback and help so that we can do this the right way.